Yeah, hi. Just wait for some 2 3 minutes. Let others join, then we can start the session. Yeah, good evening. I hope my voice is visible and the screen is visible. Just let me know if it is not. So, yeah, welcome to the Manufacturing Process Casting and Joining session 2. My name is Rakesh. I'm a PhD scholar at IIT Bombay. So, I'll be taking some brief recap to the week 2 session in this live session, and then I will solve some problems regarding that. So, I hope everyone is fine. So, before starting, so I would like to take your opinion, like how to start this session. So basically, in the last session, there was some request in the start of the lecture, discuss the problems, at what time I will be discussing the problems. So just let me know if anyone wants to know the problem, just the problems. I can discuss that in the first session. Like this is a 2 hour session, so in first hour I can discuss the problems, and then in the next hour I can take the brief recap, like the summary of the all the lectures that has been taught in this week, like in week 2. Okay, just put your opinion in the chat box, or you can directly unmute and speak. Is it okay? Shall I continue with the same model that I followed earlier? Like, shall I discuss in brief some 1 hour, then I will try to solve some of the problems. Is that fine? Okay, I hope everyone is fine with this. So I will continue with that then. Okay. So I think this week 2 is little balanced, I can say, which is composed of both numerical as well as theoretical concepts. I think in the start of the first two lectures, it is completely about the solving some of the numericals. So I will be solving in this class as well. Then I will talk some of the theoretical concepts as well. Okay. I hope everyone is fine. Then I'll start the session. So just let us have a recap what we are going to discuss in this session. Like what is the recap of the week 2? So in this week 2, there was some discussion on aspiration effect. Then there was comparison between filling of top and bottom gate system. Then there is a optimum riser design. So we'll be discussing very in detail about the riser design. Then we have means I cannot say it's a complete thing about certification. Certification is a vast subject, so there was some preliminary brief introduction about certification, then how to calculate the certification time, then the sum of the shrinkages. So all these concepts are very brief. So it's not the complete theory about certification or complete theory of certification time at the shrinkage. There is a lot, but this is course will teach you only the like introduction part of that. Okay, don't think this is the all. So there is a lot. You can go and read the literature as well, the textbooks as well. Okay, so these are the concepts that I will be discussing in this session. So let us start with just a second. Yeah, sorry. So let us start with these filling times. So what is the comparison between this? I think aspiration effect, I think everyone is fine. Uh, what is aspiration effect and what are the formulas, derivation, everything. Just have to remember, don't need to remember the derivation. You just have to keep the concept in mind. So what happens if a cylindrical razor is used, and what happens if a tapered razor is used? So that simple concept, if you keep in mind, that is fine. And the derivation is like, if you know the applying how to apply the Bernoulli's principle between 2 points in a fluid flow. So that's all. You can be very confident about this topic. Okay. So I think take out your pen, notebook, and just try to solve this problem. So this is a top getting system. So we have a it's in inches, 5 inches. Then we have a gate area. The sprue height is 5 inches, height of the sprue. So then gate area is 1 inch square. Then we have the length of the casting and the casting size. Casting is 5 into 20 into 10. Okay, just try to calculate solidification time in top as well as solidification time in bottom. Okay, this gives a complete picture about this top and bottom gating system. Sorry, not solidification time, filling time. Sorry, filling time in top as well as the bottom. Okay, I hope you know the formulas. Just revise the formulas. I have derived the TF for bottom in the last class as well as top. Just try to find and give me these two answers. Then we can compare these both of the things. Just take some 2 minutes. Then I will try to solve the problem. So if you are facing a problem with the inches and inches square, then you can convert this into your normal convention units. So 1 inch you can take approximately 2.54 centimeter. So accordingly you can take the z value as well. So that is, so this you can take 981 centimeter per second square. Okay, and then you can calculate everything. This is also in inch. Okay, just try out. Anyone with answers? Top gating, I think it is easy. I should spend some time on bottom gate system. Anyone with the answer? So 1 minute, I'll try to solve the problem. Okay, then I will discuss. So let me. Okay, so this is the question. So let me try to solve it. Height of tree is 5 inches. Then we have bottom gate area as 1 inch square. Then we have casting size, okay, that is 5 inches height, 20 inches length, and breadth is 10 inches. That is the all the data that has given to us. Okay, fine. So this is what the data given to us. Uh, so first of all, top gate. Okay. So anyone remember the formula for top gating system? No. Okay. So someone has given answer 157 seconds. Okay, let us see. So this is top gate. So top gate formula is pretty simple. So it is just V is equal to 2gh. That gives the velocity. This is the height of the sprue. That gives the velocity. Then we have the area of the gate. So time is nothing but sorry. Hope you can see area of the gate we have that is 1 inch square. This is nothing but square root of 2 times. So G value we should take. So let us keep everything in say centimeters. Okay. So 2 into 981 into the height is 5 inches. That is 5 into 2.54. This gives you the velocity. The area is 1 into 1 inch is 1 by 2.54 whole square. Fine. Then we'll get the area here. Then filling time in top is nothing but volume divided by area of the gate into velocity. That is, volume is given is 20 into 10 into 5 into 2.54 whole square whole cube divided by these two values. Let me calculate. So 2 into 91 into 5 into 2.54. So this is 157.85. Someone is giving that velocity value. Then we have the area value. So let's keep here. So this is in seconds. This will be in centimeter square. So if you keep here, sorry, this will be in centimeter per second, and this will be centimeter square. So if you keep here, then 1 by 2.54 whole square multiplied by 157.8785. Okay, this is the value you are supposed to get. Oh, sorry. 1000 multiplied by 2.54 to the power of 5 divided by 157.85. So I'm getting 669.76 seconds. It is for top filling. Okay. So did anyone get the similar answer? Just let me know. Fine. Okay. So let us do the same thing with the bottom gate as well. Sorry. So let me start the bottom gate system. So this is for top. Now for the bottom gate system. So time of filling for bottom gate is just a second. This bottom gate is little lengthier formula. Uh, yeah. So it is 2 times area of the mold divided by area of the gate multiplied by square root of 2 times g and then square root of height minus square root of ht minus h. Okay. So now I think you have to draw the diagram as well. So in this case, so for the top it has entered from here, but from the bottom you have to keep the screw from in this way. Okay. And then this height is 5 inches. Okay, and this height is as well 5 inches, and then that this height, this length is 20 by 10. Okay, this is 20, and then this is 10. I hope you can see the values. Okay, so right now, so for calculating this, let me take. So let me write the value separately. So first of all, area of the mold. So that is nothing but 20 into 10 multiplied by 2.54 whole square. You can keep in inches also. That's fine. Uh, so area part of the gate. So as you can see in this figure, so the directly they, so this area will take. They will give you the area as well. So this is the area of the gate. They will mention the area. Generally, area of the gate is the minimum area that we consider. Okay. In the given, suppose they are giving area here as well, we generally do take the area of the bottom. So if you for so someone has asked the question, that's why I'm mentioning. So if you remember the derivation that we have done, so this is the area of the gate that we have taken. That is nothing but, so this is point 0.3 and this is point 0.1. So this is the one that we have taken for derivation, if you remember. Okay. So right now area of the mold we have. So area of the gate also we have, that is 1 inch square. So that's, we have to divide. Okay. Okay. I think we have made a mistake. I think here also it is not 1 by 2.4. I think this is 2.54 directly. Okay, this is the mistake we have done. So this 2. So this will cancel. So here it will be just 1 times. Yeah, thanks for pointing it out. Let me calculate now. 1000 multiplied by 2.54 divided by 157.85. Yeah, it is 16.09. I hope you are getting the same value. Here I have made a mistake blunder in this conversion. It is not inverse of 2.5. This is directly 2.54. Okay, I hope that is clear. So let us proceed. Yeah, this is 2.54. Then we have area of the gate as well. 2z. So z value is 981 centimeter per second square. Let me change. Then we have ht is equal to hm in this case, and that is equal to 5 inches. Okay. Then we have hm. Both yeah, we have everything, all the data if you plug here. So if you see this htm and hm are both are equal, so this term will tends to 0. Okay, but if this tends to 0, so 2 times am to root ht. So this is what we left with, right? Everything has gone. Ht is equal to hm, so that term has gone. So I think you can replace. You can rewrite this method, this formula. How a into, let me write ht is equal to hm. That is the height of the screw equal to height of the mold is equal to h. Okay. So in this case, a into hm into square root of h divided by az into under root 2z. Okay. So what happens if I multiply by h and numerator as well as denominator? Okay. So this h I can write as square root of h multiplied by square root of h, right? So that this h and this one will get cancelled. So I will be left with am into h divided by area of the gate multiplied by 2 times 2z and then h. I hope area of the filling in bottom, which is similar, right? Which is also similar to filling time in bottom. If you clearly see, area of the mold is nothing but 20 times 10 and h is 5 divided by area of the gate is 1 inch square, 1 inch 2.54. This will be 2.54 whole square, whole cube, and this will be square multiplied by square root of 2 times 981 times 5 into 2.54. Okay, and which is similar to the top gating system. So what we conclude from this question is, if height of the mold is equal to height of the screw is equal to height of the mold, in this condition the filling times of top is equal to filling times of bottom. So that is what we can conclude from this numerical that was presented to us. I hope it is clear. Any doubts? Okay. Okay, so let's move on. So let us go to the presentation. So if at all, this height of the screw is equal to height of the mold, in this case, the filling times of top is equal to filling times of bottom. Just remember this. May be useful while solving some questions as well. Okay, let us move. So this is how they presented. Okay. think HT is 5 inches. I wonder how they are getting the other value. Are you guys getting the same value? So in the first case, we are getting 16. That is fine. In the second case, can anyone verify this? Okay, just verify. I will continue with the session. I think there are so more numericals. I think if at all this HT is equal to HM, I think both should like should be the same value, or it is two times. Okay, okay, okay. Yeah, yeah. I think I missed one part. Yeah, just explain. I think I missed this too. Okay, sorry, sorry for that. Okay, I think you cannot see my screen. Yeah, sorry for the mistake. So I found so what happened here. So this formula, this term will be same as top. Okay, so, but this two is in front of it. So that's why filling time in top is twice the filling time in bottom. However, we are getting 16.1, so this will be simply 32.2 seconds. Okay, this will is a nice derivation. This is applied when subjected to this height of the screw is equal to height of the mold. Okay, just keep in mind. I think rest is clear. Okay. I will not spend much time. We'll go to the next design. So for this optimum riser design, so I'll just explain here itself. It is simple derivation. So basically, one thing we have to keep in riser design is why we need a riser. Okay, so for that, so basically, so let us assume one simple casting. Okay, so we are trying to let me erase for simplicity. Let us take a top gating system. Okay, so right now we are trying to fill this with the molten metal, this complete portion. Okay, so what happens is we already discussed about the shrinkage and the reasons for the shrinkage. We will also be discussing in this session. So while we have to compensate this shrinkage, so the pattern that we use will compensate only for the solidification shrinkage, right? So, but for the liquid shrinkage, we have to use a riser. Okay, basically what we do, we just connect the other end to the top of the casting. Okay, it's not simply connected. There are some design consideration that will be taken before doing this. Okay, so that's why we'll just connect so that this will become completely filled, and we can actually see coming out. So this is like the sprue, and this is the riser, sprue, and then casting. Okay, casting is nothing but our product. Okay, so this razor, the basic condition between these razor and screw is that, so this razor should solidify, that is time for solidification of a riser should be greater than solidification of the casting. So then only this riser will, like, if whenever the casting trying to solidify, if it is getting a liquid shrinkage, so riser should be in liquid stage such that it will supply metal to the shrinkage, so that it will compensate the shrinkage. So that is the goal we have to keep in mind whenever we are designing the riser. So the time of the riser should be always be greater than time of the casting. Okay. So let us try to do that. So what is the optimum riser design? How will you optimize? So let me concentrate in this. Okay, so here h by d is the r value. So if you can like differentiate the r value with respect to vr, volume of the ratio, so that is going to give you the least like the optimum value for the riser design. So this r is nothing but h by d ratio. So what is happening, so if you see volume by surface area, okay, this is modulus, we call volume by surface area. So this ratio, if this ratio is more, then it is going to solidify slower, and if this ratio is small, then it is going to solidify faster. Okay, so how where I am concluding that is, so generally surface area, if the surface area is more, then there is a chance for the heat loss, for heat transfer to be taking place more often. Okay, so if area is more and the volume content is low, if the volume more means we have more heat content inside. If the volume is less means we have less heat content inside. So if the volume by area is more, so that is means volume is more means that heat content inside is more compared to the surface area. So the heat content inside the riser will be more, so that if the V by A ratio is more, that means the solidification time is going to take more. Okay, in that way we can remember, and this is how this is determined. Okay, yeah, we'll discuss. We will have so many problems coming up. We can discuss everything. So right now we have this. So let us take a simple cylindrical riser. So we have VR is pi by 4 d square h. Okay. So then pi by 4, we what we are doing is we are taking h by d as r. Okay. So in this case, we'll pi by d square. So in this case, what we do, we'll just multiply d and divide it with d. So we are getting d cube into r. So this is r. Okay. So this is done. Then surface area is nothing but pi dh. That is the lateral surface area, and then top and bottom surface area. That is pi over 4 d squared multiplied by 2. So therefore, if you take V by A ratio, it is going to give you this value. Okay. Then we have VR is pi by 4 d cube r, this one. And then if you keep this d value inside in terms of, so everything will be in terms of volume by area as well as r, which is the ratio of diameter h to height to diameter of the cylinder. So we are going to end up with this equation, which is nothing but volume of the riser. So now if you differentiate with the ratio, that is h by d, so if you differentiate, it is going to give you this equation, that is 1 plus 1 by 2 r whole square is in multiplied by r minus 1 by r is equal to 0. So this will go to 0 only if r is 1. Okay, so that is means h equal to diameter. So therefore for optimum riser, this diameter of the cylinder should equal to the height of the cylinder. Okay, this is very important formula for solving so many numericals. If they are asking to design a riser, the find the solidification time of a riser, then for optimum, so that is what we have to keep. So if the question mentioned optimum riser, we can take directly diameter is equal to height, and we can proceed with the formula. Okay, let us move ahead. So before moving, just an introduction to the heating the metal. So this is the formula that represents how to calculate the enthalpy or heat that is provided to these materials. So let me explain this with simple graph. For I'm taking a pure metal. This is temperature versus time. Okay, so right now, so if you see, let me let me come from the let me come from the from here itself. So this is our pouring temperature, and this is our melting temperature, and then this is our room temperature. Okay, so right now if you see, we have three regions, one, two, and three. The first region is, if you see the enthalpy formula, it is nothing but capacity heat, that is mass into density multiplied by Tp minus Tm, that is H1, enthalpy in 1. Okay, similarly H2 will be, H2 portion is latent heat, so it is just Hf, rho v Hf. Okay, that is H2. Then H3 will be, it has to come from the freezing point to the room temperature. Okay, so we'll just multiply with Cl Tm minus T naught. Okay, so we are cooling from one region, two region, and third region. If you multiply all these three, we are going to get that amount of heat that we need to supply to the metal. So it is not simply melting it; we have to melt a bit further as well, because we have to carry the metal from the furnace to the casting place. So this time also we have to consider, and there will be temperature drop. So that's why we are going to uh, pour the more metal, and also it has to feel complete casting. It should not prematurely solidify. So that is the one more reason we are going to superheat it. So we call it a superheat. Okay, this is the formula, how the formula is derived. That is the heating the metal. So let us move with the introduction to the solidification. So I'll come to this riser design again. We'll solve some of the numericals as well. So let us discuss some of these concepts. Okay, so I think everyone knows solidification. It's like the freezing of metal. So basically, when you start, so when you start from liquid, when you heat the metal, this solid is going to convert into liquid. Okay, on supply of heat. Okay, that is happening only in the pure metal. So this this temperature time diagram is for pure metal, because it will freeze at a constant temperature in which it is going to reject the latent heat into the surroundings. So we have a pouring temperature, we have a liquidous line, and we above which will be complete liquid, and then we have this local certification time, and then we have completion of freezing, that is freezing temperature, and then solid cooling. So if anyone asks what is the total solidification time, it is the solidification time from the pouring temperature to freezing. It's not till the room temperature. So that's why they mentioned total certification time, also called TST. Okay, total certification time. So this is what happens in pure metals. But if you see the microstructure, so this is how it looks when you pour a hot metal into, this is the mold, this is the sand mold, and this is the surface. So this is how the like microstructure looks like. So it's a block. So basically, let us see this. Let us say this is iron. Okay, you completely melted it, and we have poured into a mold which is of this cross section, and then dissection it, and we can polish and we can etch. So this is how it looks. So we can see at the bottom, at the interface of the this sand as well as the casting, we have some thickness. Then from there it is almost symmetric, if you see. Okay, so this happens because so whatever the liquid that is going to touch the surface, so there will be rapid cooling, so it will form a thin layer in which we will have small grains randomly oriented. Okay, then it will form dendritic structure, growing straight forward into the center, because we are having thermal gradient in such way. So at the center we are having very high temperature, and at the mode we are having the room temperature. So it is going to be cooled in this direction. So that's why the dendrites will grow in the opposite direction, and then they'll everything will get meet at the center line, and this line is called center line. Okay, and then we'll generally have a shrinkage here, that is called center line shrinkage as well. Here it is not shown. So this is how a cross section of a pure metal looks like. So there was a question. Yes, the solidification, the volume shrinkage occurs. Here also the volume shrinkage occurs. So how I'm telling, just so whenever you are free, just search this in the internet. So take pure iron, take the density of the solid, test the density of the liquid, and check whether they are equal. Take pure iron, take pure aluminum, take pure magnesium, take all pure metals, pure, then see their density in solid as well as liquid. You'll see the difference. If there is any difference in the density, there will be shrinkage happening. Okay, and of course there is shrinkage happens in pure metals as well. Okay, correct me if I'm wrong. Then let us see the alloys. For sure, in alloys, pretty sure there will be shrinkage happening. Before that, in alloys, there will be one more mechanism that is going to happen. So what is that? So one, you can see this curve, that is a freezing curve, is not at all, is a horizontal line. It's an inclined line. You can see here. Okay, so there will be no constant freezing time. Okay, see in this region as well, in pure metals we have a complete solid line. Okay, but here we have an inclined line. That means it is there will be a mushy zone. We call mushy because it looks like a paste. Okay, some paste that we see. Okay, because it consists of solid as well liquid. In this liquid as well as solid, as you see in the left side, and that is this diagram. So this right side time temperature is taken for a particular concentration, that is this at 50%. So this is called phase diagram. How this is constructed? So we'll do this experiment with 50%, with 10%, with 20%. Then we will take these points and then we put here, put here, put here, put here. Then we'll join them, and that is how we are going to get these phase diagrams. Okay. So this is nickel copper phase diagram. For a particular concentration that is at 50% copper, we are getting this type of solidification curve. The rest everything will be similar except this freezing zone, which is consist of liquid and solid. And interestingly, when you see the microstructure, it is different. So in metals, we have seen complete in this center region, there are dendrites that are growing, and we can see they are meeting at the center point. That is called center line. But what happens here is that the rest of the phenomena is completely same at the interface, at the mold interface. I'm telling because there will be liquid, there will be mold surface, that is sand surface. There will be interface between those two. At that interface, we'll have a small thickness. Here they are exaggerated, but it will be generally very minimum thickness. We'll have a randomly small grains because of the rapid cooling, followed by the dendritic growth. And then what happens is while growing, so this nickel, so in this case we have nickel copper. So let me take A and B. Let me say A is some 10%, B is some 90%. Okay, so what happens is this dendrite is made of B. So this all the dendrites will be made of that is called primary phase. Okay, these are all called B, and of course there will be some part of A, and this will be trying to reject this A which is dissolved in it. Okay, so that A will be rejected into the solution as well, and it is going to be concentrated at the center. Okay, all this rejected so this is called solute. Okay, this is called solute rejection or segregation of solute, which is going to collected at the center. And if you see here, if the solute concentration is going increasing, you can see that a melting point is getting dropped down. Okay, drastically. So that is why at the center you are going to again get a mushy zone consist of a solid grains as well as liquid of the other phase. Okay, so that is why this microstructure is different from the pure metals. Okay, I'll come to that shrinkages. We have a quantum shrinkages. We'll discuss that. So that is what solidification happens. Okay, so just remember the concept. So casting is all about the concept as well as numericals. Just remember the concept. What happens in pure metals and what happens in alloys. So this is just a very brief of the solidification. If you are interested, you can go through some other books. There will be detailed explanation on by this direction and why this dendritic growth and why this small grains randomly oriented, everything you can understand. Then and then let us start discussing certification time. Then we have a good number of numericals in this certification time, which composes of the optimum riser design calculations as well. I will discuss about the shrinkages as well at the end. So certification time is very simple. Time required for caching solidify after pouring. Okay, we have seen in the graphs as well. It is still the freezing point completed. Either it is pure metal or it's a alloy. So we have many rules, but we mostly concentrate on this Choniverse rule. Okay, Choniverse rule. So generally, you can keep B silent. Okay, Choniverse rule. Then, so what Choniverse rule tells is tells us a casting with higher volume to surface area ratio cools and solidify more slower than one with the lower ratio. Okay, that's what we discussed in the riser as well. So if the V by A ratio is more, it is going to take more time to solidify when compared to the V by A ratio lower of any such component. Okay, for the same values. So let us discuss the terms that are used. So this total solidification time is like Cm multiplied by volume to area whole power n. So it doesn't matter you are applying this formula to casting, you are applying this formula to riser, any component. This is the formula. You just have to change volume area and then C and then n values. So let us see. V is the volume of the casting, A is the surface of the casting. We can say it can be riser as well. Okay, n is the exponent usually taken as 2, and Cm is the mole constant. And you have to pay attention here how on what values or what uh, properties this mole constant depends. It depends on the mold material, it depends on the thermal properties of the casting metal, and then pouring temperature related to melting point. Okay, it depends on the mold material, that is sand, or if you're using fine sand, or if you're green sand, or different types of sand with different types of clay material or water percentage. Then thermal properties of the casting metal. Thermal properties means nothing but the thermal conductivity of the metal, dense, mainly thermal conductivity of the metal. Okay, and then pouring temperature related to the melting point. So melting point of the metal as well as the pouring temperature of the metal. Nothing but they are asking of the superheat. Okay, these are the three properties that mole constant is going to depend on. Okay, that being said, that let us quickly solve a problem. So you are going to be asked problems on, one is the filling time that we have done, then one is the solidification time. Okay, so these are the two things you need to keep in mind, as well as the riser design, as well as the gating design. Okay, these are the numerical things that you need to keep in mind while attending the exam. Okay, so let us quickly solve this problem. So I'll give 1 2 minutes. So right now it is 6:54. I will start solving at 6:56. Try yourself, then I'll try to solve. This is very simple problem. Try to solve. Okay. I think I will. You keep on trying. I will just try to solve the question. Okay. So they have given you the length, width, and thickness of the casting. So that is indirectly they are saying giving you volume to surface area. Okay. Then if the total solidification of the casting is itself, so they have given solidification 1, then they are asking for diameter of the riser so that it will take 25% longer for the riser to solidify. Okay, they did not tell you optimum riser, so you cannot take directly D is equal to H in this case. Okay, so we need to find D and H. So we need two equations in this. So let us solve them. So basically, we know only one formula that is solidification time. Total solidification time is Cm multiplied by volume by area whole square. Okay, we don't. They did not give you Cm and two, but if they did not mention, then n exponent you can take two, but Cm we have to calculate here. Okay, so let us see. Then let us try for the casting first. Okay, clear. I hope you can understand this. Okay. So and then remember this will be in minutes, not in seconds. And if you want to solve me for the values, so V by A is going to give you meter, say meter or centimeter. Say for example centimeter. So V by A is going to give you centimeter. So it is, we don't know the units of so tst will be in minutes, cm we don't know, then v by a will be in centimeter square. So the unit should be centimeters minute per centimeter square. So that is the unit of cm. Okay, this will be always in minutes, just keep in mind. For example, they are given here in minutes, but if they give in seconds, you have to convert into minutes. Okay, just keep that in mind. Thanks. Okay. So right now we have to calculate CM. So indirectly CM is nothing but total certification time divided by volume by area of the casting. So that is this. So anyone calculated CM value by now? No. Okay. So we have 3.5 divided by, so I'm getting 50,800 divided by 200 into 100 into 18. So that is 3.5 divided by 50.22. So that is going to give you 3.5 divided by answer, that is 0.069 minutes. It's nothing but 4 seconds. Okay. So this is the value of CM in casting. So we know one thing. So what is that? So they have given in the question, it's a sphere, right? They said it's a sphere. So we know area of volume of the sphere is, and then area of the sphere is, okay, if you take this ratio, so we are going to end up with 4 pi r square r, that is r by 3, right? If you take in diameter, r is equal to d by, that is d by 6. Okay, d by 6 is the v by a ratio. So now it is, so we already arrived at the final answer. So right now we have cm value. Cm value will be same for both the things because it depends on the mode properties. So tst for the riser is cm, we have 0.069, and then v by a ratio is nothing but d by 6 whole square. And then they said diameter raise, so that it will 25% longer for the riser to solidify. So 25% longer means it is 1.25 times the 3 minutes. That implies d is equal to, please try to solve, I'll give the answer. 1.25 multiplied by 3 divided by, okay, this is 3.5. So 1.25 multiplied by 3.5 divided by 0.069, that is 63. So we have diameter is 47.77 millimeter. Okay, so I'm getting 47.77 millimeter. Just note the value who are solving, then we can, you can check later because we have more numericals to practice. Okay, I'm moving on to the next question. You can stop if you're solving. You can try it later. So let us see the next question. Okay, the answer for this is 47.77 millimeters. So that, let us see the next question. So a cylindrical riser is to be used for sand casting mold. For a given cylinder volume, determine the diameter length ratio that will maximize the time to solidify. Okay, so they are going to use a cylindrical. Nothing is specified. No numericals. Nothing. So they are just saying a cylindrical riser that you have to use in the sand casting for a given cylinder. For a given cylinder volume, determine the diameter to length ratio. Nothing but d by h ratio that will maximize the time to solidify. Okay. Solidification time maximize. So this is nothing but say some ratio r, then differentiate with respect to r, and the value should maximize. Okay, that is what they are asking you. Okay, let us solve. To minimize the time, I'm just showing you the derivation. So let us start with the first line itself. To maximize the total solidification time, V by A ratio should be maximized. Okay. Then we have a cylinder volume, we have a cylinder area. If you sub expression learn for the volume equation, the area equation. So what we do is we write volume in terms of length. That is L is equal to 4V by pi d square. And we try to submit this L in area. So why we are doing that? So that we'll get this, we'll try to avoid this L value. So in the final equation of area, there will be no L value. So now we'll differentiate this with area with the diameter, so that pi d minus is equal to 0. Then when you try to rearrange, will get a value for diameter. Okay, what we did? We changed the volume in terms of L, and we try to submit it in the surface area, and then we try to differentiate the area with the diameter. Of course, it has to be reduced to increase the solidification time. So finally, we got this. So if you want to do, you can try to differentiate this twice and then see what is the value coming. If it minimum negative means, I think it is maximizing. Positive means minimizing. Here I did not do. Uh, of course, it's straightforward. Then we got the value of d, that is 4 mu by 4.33. When you substitute this d value in L, you are going to get this the same value. You see, 1 and 2 equations are both are the same. That means if diameter to length ratios are equal to 1, In that case, the time for solidification will be more. Okay, if you take a cylinder, if it is diameter and length both are same, then only it is going to maximize the time for solidification. Okay, that is also what we try to discuss here, in which we got diameter is equal to height. Okay, that is, just keep in mind these two values. So then let us try to solve this problem. So a cylindrical 6 centimeter diameter, 6 meter high has to be designed for sand casting mold for producing steel rectangle plate of this dimensions having the total solidification already. Determine the total solidification time of the riser. So just see how they are framing the questions. Now you need to find the time for solidification of the riser, not the casting. Okay, but you already know total solidification time is cm multiplied by volume by area whole square. So this value will be same for the riser as well as the mold at the casting. Okay, so let us try. Yeah, hello. Hello. I think you can hear me. Can anyone confirm that, like whether you can hear my voice or not? I hope you can hear. I am continuing the session. Just let me know if you have any problem. I think I am facing some problem with the existing laptop. Okay. So what I'm discussing here is to find the solidification time for the riser. Okay. So now determine riser. So now we can find CM directly. CM is nothing but 140 divided by 2 times this. So if I would calculate this, so I'm getting CM as 3.001 per centimeter square. Okay, I think this is fine. Then let us calculate the total solidification for the riser. So TST for riser is 3.001 multiplied by, so volume by area. So we have given a cylindrical race of 6 centimeter diameter and height. So D equal to H. Okay. So I think it should be D by 6 whole square. So just verify it should be divided by H. So volume by area is volume is pi by 4 d square H is equal to D. So it is pi by 4 d cube divided by pi d square, that is pi d into H plus 2 times pi by 4 d square. Okay. I think if you solve this, I think you're going to end up with d by 6 or d by 5. Okay. Uh, it is pretty straightforward. You can try. I think pi d cube d cube. So you are left with d by 4 divided by 1 plus 1 by 2. Okay, that is d by 6, right? So d by 6. Now d is nothing but 6 in this case. 6 is cancelled, so it is going to be 3 minutes. Total solidification for razor. Okay, this is you can calculate, otherwise you can do this. So just remember, it will be d by 6. Even if it is a square, it will be a by 6. If it is a sphere, it is going to d by 6. So this is simple derivation. You can try the b by a ratios of different types of geometries. Let us quickly calculate one more problem here. So two castings of the same metal have the same surface area. So remember, it has the same surface area. One casting is form of sphere and one is in cube. What is the ratio of solidification time for the sphere to the cube? So they're asking you total solidification time of the sphere to the total solidification time of the cube is what? If subjected to surface area of the sphere is equal to surface area of the cube. Okay, so we know that v by a ratio of the sphere is d by 6, and then v by a ratio of the square is also, let us say a length of it is a by 6, that is a cube by 6s square, ss 6a square, a cube cancel will end up with 6, so that is going to be a by 6 and is going to be d by 6. So right now what is there said, the surface area of the sphere is nothing but 4 pi r square, that is nothing but pi d square, right? Okay, and here the surface area is 6s square. Okay, and these both are equal. So if you see here, if you take the ratio of these two, ratio of pi d squared by 6s square, that is nothing but ratio of surface area of the sphere divided by the ratio of the surface area of the cube. So is equal to 1 as per the question. So now if you rearrange this, you're going to get the, we want to sphere to cube, so d by s whole square is nothing but 6 by pi, and if you take the square, it will be root of 6 by pi, and then total solidification time is nothing but CM that mole constant will get constant, then v by a whole square by v by a whole square of the sphere to the cube. So now v by a is nothing but d by 6 in this case, that is d by 6 whole square divided by v by a is nothing but a by 6. Okay, now if you rearrange this, d by a whole square, what is d by s, sorry, yeah, it is a only, d by a, d by a whole square, that is nothing but by 6 by pi. Okay, 6 by pi is the answer. So this is also a way to test your like derivation skills, something like that. In if without any numericals, you can actually end up with a solution like this. Okay, they can play with any type of geometry. In this case, they have the sphere and cube. They can ask sphere and cylinder, and then different things as well. Okay, this is one more type of question. Then let us start with the final topic of the day. So I'll see if there is any questions. Just put, you can put in chat if you have any doubt. I will try to explain that there itself. Okay, so let us see what is the shrinkage. So you already know, we already discussed this in the last question. So shrinkage of occurs in three steps. Okay. So one is due to the liquid contraction, one is due to the phase change, and one is due to thermal contraction. That is while it is cooling from the freezing temperature to the room. Okay. So yeah, I think you can hear me, right? Okay. So okay, fine. So this is what shrinkage is happening. So it happens in three stages: during liquid contraction, during phase change, as well as due to the thermal contraction. That is between the freezing point of the solid to the room temperature of the solid. Okay. Then this is a simple diagram that will explain you the complete part of the shrinkage. So if you pour a molten metal, initially whichever is touching the mold surface will cool faster, and then at the center it is going to be the hotspot. We call it as a hotspot, which is going to solidify at the end. So that's why we are getting a shrinkage at the center. If you see, because it is open to atmosphere, so it is not cooling faster compared to the sides of the casting. So this is how the shrinkage happens. Okay. Similarly, so this is some of the linear shrinkage of the different types of metals. You can see aluminum alloys 1.3, brass, yellow, cast iron, gray cast iron. Then you can see nickel, you can see magnesium alloy, you can see magnesium itself. You can see tin, zinc, steel, chrome, everything. But there is an exemption, that is graphite, that is gray cast iron, especially cast iron with the high carbon content. So what happens here is it's not that it is not shrinking. It will shrink, but it is very negligible due to the process called graphitization, in which this hard phase, that is martensite, something like that, hard phases will convert into this graphite, uh, like the graphite flakes, or graphite phases uh, in that phase, in that alloy, and it is going to counterattack this volumetric decrease. So if you see up to 2 feet, it is 0.125 inches per feet, but beyond 4 feet it is 0.083 inches per feet, which is almost very less. Okay. So that is why we generally will not consider cast iron for linear shrinkage. Means we will not provide the linear shrinkage for gray cast iron especially. Okay, so that is what explained in the thoroughly followed in the textbook. So let us see some of the caching process. Then I will try to complete this caching process. Then we'll go to the sand casting and cell mount casting. Once they are done, investment casting, then we'll go to the problem solving. So I'll be explaining very quickly one by one. So we have basically two types of process. One is the expendable, one is the permanent mold. I think you already know about the advantages. Expendable mold, we have every time we have to break the mold, so the production rate will be very less. So that's the main concept, means main limitation for the expendable molds. Whereas in permanent molds, for mass production, we can use it as this process. And disadvantage is geometrically limited by the need to open the mold. Okay, but sand casting generally is used for whatever the types of different shapes of the product. Okay, that is the expendable. So under expendable molds, we have different process. One is the casting, sand casting. One is the shell molding. One is the investment casting. Okay, so let us see what happens in casting. So you already know, you're going to make a pattern. We're going to make a core if necessary. We're going to mold the metal sand. Then we are melting the metal and pouring. Then we are going to remove the metal from that. We are going to felting, which is removing of unwanted portions. Then we are going for testing and inspection. Okay. Yeah, yeah. I will. By this night, I will upload everything. Okay. So then we are going to the properties of the sand. You also know we need strength, we need permeability, we need thermal stability, we need collapsibility, we need reusability. and this reusability will be limited. We cannot always reuse it, so there will be small uh, while you crush that you once the mold is made, you have to break it. Then the broken molds will be crushed into fine sand, then reused again. While crushing, so there will be these small grains that are formed. So this is not good for the permeability in terms of permeability aspects, and there is a chance it will actually enter the casting as well. So that's why we'll after some time we'll throw out sand. So it should have a good reusability. It should not form that small grains of sand. Then collapsibility. While if you pour a metal, so it has to ability to expand without cracking. Then while sorry, it should have a good thermal deformation. That's what this collapse will limit. Then thermal stability means it has to resistant to crack when hot molten metal is poured into. Variability, I think you are very known about its strength as well. So last class we have discovered the strength, that is tensile as well as compressive strength, if you remember. Okay. So in that case, so generally between 2 to 4% of moisture we use what moisture, in which case this is limited by the tensile stress, not the compressive stress. So we generally have to take care that. So compressive stress around some 5 to 6% of moisture, compressive stress will be higher. Around 3% of moisture, tensile stress will be higher. So accordingly we have to calculate. So both are necessary for designing this model. Okay, I will come to the doubts. Okay, then we'll move quickly to the shell molding. So these are some of the expendable modes in which we have to physically break the mold to take the casting out. We have a shell, we have a vacuum molding. Shell I will explain now. Vacuum molding is nothing but we use this vacuum machine to feed the metal into the casting so that it will go into all the parts of the casting. Then we have expanded polystyrene process in which will not keep pattern, we'll keep a styrofoam so that when metal enters, it will directly melt away with the styrofoam. Then we have investment casting that I will be explaining. Then we have plaster mold and ceramic mold casting. Okay, let us go over it. So shell molding. So in this, what happens is this is the process. In first step, we have a sand with the resin binder. Resin binder will cure when you heat it. So what happens? We'll heat this pattern. Then we invert the box so that this sand will get into the will fall on the this pattern, and we touch the hot pattern plate so that the thing that is touching the bottom will get hot enough and get cured. And when you re-invert it, so we'll have a thickness formed here. So what happens? We'll take it out, we'll cure it, and then we'll assign like in this case in this fashion. And then finally we pour the metal and we'll break the mold and we'll take the casting out. So this is how what shell molding means. So in this process you can see. So this is a shell. This is a shell, two shell mold, and we have a design in this. We just enclose it in this fashion, and then we pour the caching and we open it. Okay, that is how two shells are used. So these are the advantages and disadvantages. This shell is light and thin, which is 5 to 10 mm. Thermal conductivity different sand. Okay, these are the depends on thermal conductivity of different forms of sand. Advantages is complex shape, better dimensional accuracy, better surface finish, significant reduction in cleaning, machining, and finishing, because you are going to produce a net shape product. But when it comes to the disadvantage, it has lower permeability, decomposition of sand, very with this high volume gases need very good ventilation, and these are the some of the products that are being manufactured using this shell molding. Okay, so if you want to remember advantages and disadvantages, just remember the casting process. From that, you can deduce all these things. So let us come to investment casting. This is very famous casting. I suggest you to watch the video that Professor has shown to get better understanding of this investment casting. It is very simple process. So basically, what we do is we use wax in this case. So basically, in the first step, we use a wax and we create these molds for the casting, and then we attach them into a central sprue. This is the central sprue, and then we attach these things in this fashion. And then what we do is we put in a flask, and then we pour this investment casting or the mold inside, and then we heat it. So once you heat it, and this is the nothing but a, we can do plaster of Paris, we can take any ceramic slurry as well. Then we when we heat it and invert, then this wax is going to come out. So you can actually reuse the wax as well. Then we are going to pour the molten metal. Then we are going to take it out and we are going to cut the required pattern. This is how a simple investment casting looks like. We can directly, this is the pouring section. We can directly pour, or we can directly dip in ceramic that is called stucco coating. We can directly put in the ceramic coating two, three, four times, and then we can get that required thickness. This is how the investment casting is made. Okay, these were the some of the advantages and disadvantages. So investment casting, if I see turbine blades are made of investment casting, and then these are the advantages and these are the disadvantages. One thing is this is also called lost wax process that you need to remember, and we are going to get net shape products. Okay, wax can be reused, close dimensional accuracy, great complexity and intricacy can be cast because of this wax, which can easily go into any pattern, any intricate shapes as well. But main disadvantage is it involves so many processes. See, we almost have eight process to get a product out, and so that is the reason it is a relatively expensive process. Okay, that is what this investment casting is. So now let us take some 3 minutes break. So it is 7:27. So we can meet at 7:30. So I will try to solve these problems. Then we can call the day.
Hello, sir. Hello, sir. Hello.
Yeah. Hi. So let us continue with the problems. So before that, I will answer this question, sir. How to determine the diameter of riser when the riser height is only given? So they will mention which is the optimum riser or not. If it is optimum, you can take diameter is equal to height and you can solve the problem. So that is the one way of doing it. Otherwise, it is very difficult to find the. So and otherwise, there is no way to find this diameter of the riser. So there will be some other options will be given. For example, they can give you the solidification time and the mold constant, and then you can ask for this diameter. Okay. So unless something has to be given to solve the question. Okay. Let us start with. So take time. Take 1 or 2 minutes to answer these questions. Then I will solve. You can put in the chat the answer, or you can directly unmute and speak. Either way is fine. Okay. Try to answer. I will. It's better if you even if you answer wrongly, you can remember the answer correctly, and then you can like correct yourself. Okay, let us see. So in first question, they're asking total certification time depends on. So you already know the formula, right? It depends on the volume of the casting. It depends on the area of the casting. Both area and the volume get casting. Yes, option C will be the correct answer, right? Because if you remember the certification time, it is CM divided by the area whole square. Of course, it is surface area. So I think they have not mentioned this surface area. So we are not sure whether it is surface area of the casting. So still, so we can go ahead for now. We can go ahead with option A because they are not mentioning the surface area. That is one. But obviously, finally, it is going to be the surface area, right? So option C also might be the correct answer. Okay, so option A and both A and C both will be the correct answer. But most see you can go ahead if not mention anything because in this case it no need to explicitly mention which service area, which area. So it is going to be the surface area only. So that's why we can go for option C as well. So if nothing mentioned, you can go for option C as a first priority. Then you can go for option A. Sorry. Okay. Okay. So then let us see anyone with the answer for the second question. So they are asking volume to area ratio of the casting related to the volume ratio of the riser itself should be. So generally, you can indirectly they are asking what is the solidification type of the casting to the what is the solidification of the riser. What do you think? Time should be more for this compared to TC. So this should be smaller, right? It should not be equal as well. It should be smaller. So option E is the correct one. If it is equal, what happens? Both will solidify at the same time. So there is no purpose of providing riser. So it's already be smaller. So that means it's less than one. So DC is here. So solidification time of the riser is always greater than solidification time of the casting. Okay. So option E will be the correct option in this case. Clear? So let's move to the next one. Try to solve this. Try to answer the question.
Third question answer is B.
Can you speak again? Sorry. What is the answer for question three?
Question 3 answer D.
Okay. For four.
4 is 4 questions answer B more than.
Okay. Fine. Any other answers? Okay. So I think if you remember this derivation regarding this aspiration effect, so if you see some, I have written something like P2 is equal to P3 minus Hg, sorry, H rho, right? Something like this, if you remember. So this is what they're asking. The quantity of gas that can be aspirated into the modulus is nothing but this value, which is the product of the screw length, that is H, and the metal density. So option D is the correct answer. Then for the fourth question, similarly, I have derived a derivation, if you remember, for optimum riser design. I'll just quickly show you. Yeah, this is optimum riser design for a cylindrical sample. Okay, we took the BPA ratios and we tried to minimize. So we ended up with D is equal to H. Okay, the diameter to H ratio is 1 for optimum riser design. Okay, that is what they're asking you. Okay, it is equal to 1. Option C is the correct answer. Okay, diameter is equal to H, optimum riser. Clear? Okay. So let us try to solve this. It's a numerical question. It is same, right? So we already discussed for optimum diameter should be equal to height. Okay, they are asking you raise up cylindrical shape. So what is the volume of the cylinder? is nothing but 5/4 d square h. In this case, diameter is equal to height, that is 5/4 d cube. That is pi by 4. They are asking even centimeter cube. We just remove the units. So pi by 4 d is radius is given 15. So diameter is 30 mm. Nothing but 3 centimeters. This is the value. So I'm getting 21.19 centimeter cube. Okay. I hope you are getting the same value. So let us move to the next questions. Anyone with the answer? Okay. Let us try to solve. So they have given a steel rectangular plate of 4 by 7 by 1 centimeter to be cast, and they have given a solidification time as well. They are asking you the mole constant. Okay. Oh, sorry. Yeah. So this is a very straightforward question, I can say. That is total solidification time is mole constant multiplied by volume by area whole square. So now we need Cm. So we can rewrite this formula in terms of Cm is equal to Tst divided by volume by area whole square. Right? So now they have given 90 seconds, but it gives you the units in minutes. So you have to convert this into seconds. So 90 seconds means 1.5 minute, right? So 1.5 divided by volume by area. So we have 4 by 7 by 1. So it's 28 divided by 2 times 28 plus 7 plus 4 whole squared. So if you do this, you're going to get the answer. So 11.64 minutes per centimeter square, right? Anyone getting the same answer? Fine. Okay. I hope everything is fine. I'm going to the next question. Very straightforward question it is. Any ideas? Any ideas? No? Okay. C. Okay.
Seventh question answer is C.
Okay.
Eighth question answer is B.
D.
B.
B. Okay. Good. Okay. Since the solid phase has higher density than the liquid phase, it causes shrinkage, solidification shrinkage. Yeah, that is true. The ratio of time to fill the mold cavity with vertical gating and the time to fill the mold cavity with the bottom gating is 3. No. Any other options? D. 0.5. So they are asking you the ratio of time filling with the vertical with the bottom. So we know that time filling with the vertical is always greater than time filling with the bottom, right? That we know. So this ratio will always be less than 1. Sorry, it should be the reverse. Okay, this ratio will always be greater than 1. Okay, that is sure because this is more. So it will be, so you can strike off option D. It's not 0.5. Then, if you remember, so this is not correct way to answer. They have to say that height of the what is that? Height of the sprue is same as height of the casting. So if you remember the derivation, uh, so what happens is solidification for time for pouring for bottom gate is 2 times time for pouring for vertical system. Sorry. I think I made a mistake. This is not the. I think here itself, if it is TF is greater than 1, means more than TF, so this ratio will be less than 1, right? Always. So in that way, you can conclude D is the correct option. It is like a simple way to answer, but if you want to find the reason, so this is how it happens. So time of pouring for the bottom is almost twice the time for vertical gating system. If H is equal to Hc, or else in any case, if you take it is always be the case. It is always true. Why? I will show you. See this is the formula for bottom gating system, right? So we have a this negative term in this. Let me so negative of this HT minus HTM, and we have a multiplication of 2. Okay, so that is the one reason we are always getting this value more than this top gating systems. So in if you see in top gating system or vertical gating system, it's very simple. It is volume divided by area into velocity. So volume is nothing but area into height, and then this velocity is nothing but square root of 2z into height, right? Square root. So if you see in this formula as well, AZ is constant, 2Z is there, AM is there, except under root HT. But we have a big value of 2. This HT minus is going to be less compared to this big value of 2. So that is one way of looking it. And the final way is that it is pretty clear, right? So if it is a top gating system, We have very higher velocities to fill the mold cavity. Whereas in bottom gating system, uh, we're always filling from the bottom. So we have to actually overcome this weight in order to push the metal inside. So this is always going to be lower velocities compared to this top and then bottom. And then if you see the mixed gating system, it will be in between. That is the answer for this. So it is going. The answer will be zero point 0.5 in this case. Okay. So let us move quickly to the next question. Spend some time, take 2 minutes and solve this question. Yeah.
Answer is A.
A. Okay. Okay. I think everyone is pointing towards A. I'll wait. Any other options? Yeah, thanks. So let us see. So this is about Johnny's rule, right? So we'll just write the formula for simplicity, then we can is cm multiplied by volume by area, surface area whole square, or n. Okay, let us keep n for general. So now, first one is mold material. So they are asking about mold constant, that is cm. It depends on the mold material. Yeah, true. So one is true. So you can directly strike off B as well as D. We are left with A and C. Then razor volume to area ratio. No, right? It does not do. Then we go next. Volume to area ratio of the casting. No, that is also false. Then we go to thermal properties of the casting metal. Yes, true. Right? Thermal properties of the casting metal also it depends. If you remember. Right? Then from this fourth one is correct. So you can directly remove option A. So we are left with option C. So that will be the correct option. Let us see the next one. Flowability of the model metal. Wrong. Pouring temperature of the relative to the melting point. Yes. So only three properties it depends. That is mold material and thermal properties of the casting metal, and then pouring temperature related to the melting point of the casting material. Okay, these are the 3 points that your mold constant depends upon. So option C will be the correct option in this case. I have discussed. I'll just show, so you'll be confident enough. So I have discussed this when I'm discussing this. Yeah. So if you see this mole constant, it is depending on the mold material, thermal properties, and then pouring temperature related to the melting point. Clear?
Okay, sir.
Yeah. So let us move to the final question. Then, yeah, take some time. So in numericals, you should take care of the units. You're asking in meter per second. So any answers? Any answers? Okay, I'll start. So for sand casting, the sprue height was kept at 60 mm. Okay, so height of the sprue is 60, right? Then then they want what should be the flow velocity in meter per second of the movement method to obtain defect-free casting. Acceleration due to gravity is 9.15. Round up to the one decimal place. So so this is just to trick you. This obtain defect-free casting. Okay. So we are having only one value. Basically, we are having height of the screw, and then g. Of course, g is available. So from this, how do you find the flow velocity? So flow velocity is same. The formula doesn't change. Under root 2gh. So this flow velocity is only depend on the z and h. We only need these values, and we have already have these values. So this is like a tricky up to the defect free casting. So it is not depending. Velocity is not much depending on this defect free casting. It depends on so many other parameters. So we can directly go ahead with this. So we have two. We can use 9815, and then the height is given. So we are getting 1085.265. This is millimeter per second because everything is millimeter. But they are asking you in meter per second. Okay, so it will be 1.085. So this is how we go ahead with these numericals. I hope you got some confidence on this how to like solve these problems on pouring time, then solidification time, how to calculate the shrinkage. Okay, and you also got some understanding on the types of like what is happening in what is the processing of casting and what are the different types of castings. And I appreciate that you are attending these lectures, and let me know if you have any doubts. So you can ask me doubts in the starting of the lectures. So we'll meet in the next week. If you just go through these week sessions, if you have any doubts, just ask me in the starting only. So I will be waiting for some time for other people to join. Meanwhile, you can ask me, and you can tell me if you want to cover any other topics as well prior to the classes, so that I can take that and then solve some of the numericals or take some theoretical lesson as well. Okay. Thank you for joining. We'll meet in the next class. If you have any doubts, you can ask simple doubts. I can clarify right now. Or else, we'll meet in the next class. Thank you. Okay. I'm closing the session. You can leave. Thank you.